what we have in GATE 2026. So GATE exam is an exam which is like a common platform to assess everybody who have passed through the engineering. So we are focused on aerospace engineering. So GATE AE 2026, tentatively it will happen on, there is a tentative date, will happen on second week of Feb. Okay. Every year it happens in mostly second week of February. So that will be February 2026. We will be expecting the GATE, the second week. It's probably Saturday or Sunday. Fine. Its question paper will have 65 questions. That is also subject to change. They can change this. Okay. But from a long time, they have fixed on this particular thing. So it has two categories. We'll be teaching each and everything that is there in the syllabus, even the math and aptitude also. So it has general aptitude. It carries 10, it will have 10 questions, which carries 15 marks. And you have a technical section. So the technical section is your whole engineering. You will get 55 questions from that. It carries 85 marks. Okay. So this paper, it will have 5 questions of 1 mark each and 5 questions of 2 mark each. And in this, you will have 25 questions of 1 mark each plus 30 questions of 2 mark each. And the category, so question types, what you can say, has 3 categories. Hope I am audible to all of you.
Yes, sir.
Okay, question types have 3 categories. The first category is called as MCQs. You will be having negative marking on this. Okay, so it carries negative marking. So negative marking of 1/3 of the mark. So if you do a mistake of 2 mark question, 2/3 marks will be deducted. If you do a mistake of 1 mark question, 1/3, that is 0.33 marks will be deducted from your positive marks. Then the second category you have is MSQ. So in this MCQs, 1 answer will be correct. Only 1 answer will be correct. Whereas in MSQ, 1 or more than 1. 1 or more than 1 will be correct. Fine. Then you have the third category. This last, second and third category, they don't carry any negative marking. So this will say numerical answer type. So it will be a kind of numerical value which you will fill in the blank in this. It will be a blank. Fine. Can I go ahead, everyone? Fine.
Yes, sir.
Okay. So for typically for what I suggest for general aptitude, 2 books. For general aptitude, you please have these 2 books. One is, a lot of people in our country have bad English. So first would be that having good grammar. Okay, so my first suggestion would be having a book called, you just look at the spelling. I'm not sure about this. Wren and Martin. It's a English grammar book. Right? It helps in many ways. It will be good to have that book. Okay, it comes with solution also. You just check on the LibGen. You will get a pirated copy of it. Okay. Then you have both the books I'll share if you don't mind. quantitative aptitude by R.S. Agarwal. This also comes with solution manual. I'll share the solution manual with you. Okay. So today we are going to start a topic called flight mechanics. Okay. So we'll be having sessions. I'll just divide the every week into this Monday, Tuesday, Thursday, Friday. Okay. So Thursday and Friday, Monday and Tuesday first we'll see. So these 2 days, so each class timings is 6:30 p.m. to 9:30 p.m. Okay. Monday and Tuesday, both days, we will have flight mechanics. First, we'll begin with flight mechanics. Today we are starting this. So it has 2 parts. I'll discuss that later. Okay. And Thursday and Friday, we will be starting gas dynamics from this. So one chapter that is left out for the previous batch, finite ring theory, and the small part of boundary layer, we'll cover up that later with in extra days. That is probably some other Wednesday or extra schedule I'll do. Whereas we'll go ahead with this flight mechanics today. Okay. And after gas dynamics is finished here, we will start something called rocket propulsion. Or here on Thursday and Friday, we'll have engineering mathematics. Okay. Whereas once this flight mechanics, in which you have 2 topics, and it's huge. The weightage of marks will be huge from both of these topics. So you have aircraft performance. Once we cover aircraft performance, we'll be going for airplane stability and control. Okay. Once we finish this topic, then we'll do rocket propulsion. Then we'll go for what is called as aircraft propulsion. Right? Okay. Hope you all are fine with this. Everybody?
Yes, sir.
Okay. So once we finish these topics, then we will go ahead with the remaining topics, like the other left out subjects. Can we go ahead, everyone? Hope I am audible.
Yes, sir.
Okay. So we will begin with this. After this, we will be doing the rest of the topics, like again, those who have missed strength of materials, then mechanical vibrations and all will start here. Okay. Then you'll have the other topics like aircraft structures. Right? Or probably aircraft mechanical vibrations in aircraft structures. And then we can do the rest of the other things like aerodynamics again. So let's start with this one, aircraft performance. Okay. Write a heading, aircraft performance. It's a flight mechanics part. Aircraft performance. From this topic, you can expect the marks from 9 to 11 marks from this topic alone. Okay. So it has typically 2 parts, steady and unsteady. So before we begin any steady or unsteady, we'll have chapter 1 called atmosphere. And then we will begin with steady and unsteady. So here you can write steady aircraft performance. Write this. Steady aircraft performance. In steady aircraft performance, we will be doing we'll begin with our first topic. That is our chapter 2 will be basics of flight mechanics. So what is lift, drag, mean aerodynamic chord, mean geometric chord, several other camber characteristics, what our flaps will do, what are control surfaces, all those things to do. So probably in next lecture we'll cover up that. Okay. Then we will enter into straight and level flight. Straight and level flight. Then we'll be going for something called as gliding flight. Gliding flight is called as the power of flight. Then we have climbing flight. Then we'll be going for next topic called ceiling. This has two topics. One is called as absolute ceiling and service ceiling. Okay. Hope you guys are noting this. Everything you note, guys. Parallelly, you make a habit of noting down each and everything. You will write your own notes. Okay. Can I go ahead, everyone? Guys?
Yeah, sir.
Okay. So after we finish ceiling, we'll be going for something called as range and endurance of an aircraft. So after range and endurance, we'll be doing, or before range and endurance also we can do this. This is called turning flight. So it has again three categories. One is level, pull up, and pull down. So we'll be doing this three category of flights in this turning flight. Okay. Then we'll be doing a topic called VN diagram. Okay. So this is our actually the steady performance, aircraft performance, what we'll do. Then coming back to this, again under the main aircraft performance, we'll have unsteady aircraft performance, or you can say accelerated aircraft performance. Accelerated or decelerated. So, but that is, once you are having acceleration or deceleration, it's called unsteady aircraft performance. So in its accelerated aircraft performance, again you have two topics. In this should become your chapter 10, that is called takeoff performance. Okay. Next you write landing performance. Okay. Can I go ahead, everyone? Hope you all noted.
Yes, sir.
Okay. You write references for this. The first reference for this is Introduction to Flight. Introduction to Flight by John D. Anderson. Okay. Then the next book is this book. I will share this with all of you. Almost every book we have a soft copy, so no need to worry about buying a hard copies for this. Okay. Aerodynamics for engineering students. I'll share this all the books in a drive. with most of you have done that. There is a scan copy available with it. This is a 1983 print. Okay, it's not available in many colleges. Even in IIT, we have a kind of half copy only. It's a wonderful book. People know about Houghton and Carpenter, but Houghton and Carruthers is an amazing book because the title is aerodynamics, but it has very nice aircraft performance as well as some good part of airplane stability and control also. Okay, so Houghton and Carruthers, Carru, Carruthers. Okay, then the third book that you should be using is Performance and Stability of Aircraft by J.B. Russell. Then there are other books also. Okay, like you can make use of something called as Bandu and Pamadi, but that will take you to another level. So if you want to go for further higher levels, you can refer to books like Aircraft Performance by Maido Sarlas also. That's a slightly tough book. Okay, so this would be enough for you guys. Apart from this, you can use 1000 solved questions and answers by Keith Williams. That is also a nice reference. Okay, can I go ahead, everybody? Guys, can I go ahead?
Yes, sir.
Yes, sir.
Okay, so let's start. So we'll begin with some basics of, you write airfoil, nomenclature. Airfoil nomenclature. I'm assuming that you are just a 12th pass, you don't know anything about aeronautics or flight mechanics. So we are starting from the scratch, assuming you don't even know what is called angle of attack like that, or what is Camber Line and all that. I'll quickly take you through all the basics step by step. So don't need to worry about whether you know or not. I literally don't care about it. Okay, I'll ask you so that I'll know whether you stand at that level or not. Is that fine, everybody?
Yes, sir.
What is a chord line, guys?
The line which connects any two curves.
Line which connects into
Two curves, sir.
two curves, or a line which, see, generally when you say a chord, if I have a curve, okay, if I have any curve and if I draw a line, what we call this line? A straight line which intersects at 2 points like this. What do we call this line? We call it as secant, or we call it as a chord. Okay, fine. Can I
Yes,
go
sir.
ahead? It's
Yes,
not
sir.
two. It is not the two curves. It is a straight line which intersects the curve at 2 points. That is what is called secant. Okay, or you can say a chord. My interest is, if I have an heading as airfoil, I will be interested in what is your chord line. Can you rephrase your statement again?
The line which connects the leading edge and trailing edge.
Okay. So there again starts a confusion again. Suppose I take my airfoil. Let me take some nice airfoil for you. Okay. There will be a confusion like this. So a typical confusion that usually arises is, I'll have a line like this and I have another line like this. Okay. So or one more line also I can take. Let's take lines 1, 2, and 3. Okay. So you have line 1, you have line 2, and you have line 3. Which line is your chord line? All are connecting the leading edge and the trailing edge.
Drawing a circle in the leading edge will show a result, sir.
What result exactly it shows? If I draw a circle,
Yeah, the leading in design point of view, I'm saying.
yeah. I'm also talking in terms of design point of view. I made one circle. Then which line is it?
None of these.
Why?
Well, none of these are passing through the closed figure.
Which closed figures? We
Not
are
that closed figure. The airfoil itself, right?
yeah. These all are having this, right? We are interested till here, right? At these points. So see, we will draw a curvature using the circle. We can get this kind of curvature. Let me cut this. So we will get the curvature at the leading edge. Okay. So the center of this curvature, we will find out the center of this curvature. Let this be the center of this curvature. Okay. So two things you can mark. One is the center of this curvature. Another is center of this circle. Okay. These two things you mark. Fine. So a line which passes through the center of curvature of the leading edge, which is this. Okay. Can I go ahead?
Yes, sir.
So this line passed actually through the center of curvature. So you write a heading, chord line, and you can draw this. You write a heading, chord line. And write. Chord line is a line. Chord line is a line which joins the leading edge and trailing edge is a line which joins the leading edge and trailing edge of the airfoil and passes through the center of curvature of the leading edge. So you can draw this. Draw one line which is passing through the center of curvature of this. Okay. And then this is your chord line. You can say this is your chord line. And this length is what is called as chord length in the trailing edge. So this whole length is your chord length. Okay. Can I go ahead, everyone? Hope you made that. Ashwin, you guys did this already, right?
Yes, sir.
Fine. Just bear with me for some time. There are some new joinees too.
Sure, sir.
Take it as some small revision. I'll add up new things, obviously. Like not, that's my usual behavior. Every time I do something, I'll add new things. Okay. So right next, everybody noted this? Kishore? Brinda? There is a mute, unmute button. You please use that and respond.
Yes, I have noted.
Okay. Write a heading, Camber Line. Write a heading, Camber Line. Now, let's draw the same airfoil which we have here. Okay. Let me copy this. For this airfoil, I want to know where is my camber line. So what I do is, one of the simplest ways is you can draw some set of circles and get the centers of these circles. So basically a mean camber line is a line which divides the airfoil into two equal parts. Okay. It divides the airfoil into two equal parts. So you can draw randomly some circles touching the upper surface. Okay. In fact, you can draw the first circle, that is nose radius circle, then next circle like this, or then next circle like this. You fill the whole domain with these kind of circles. Do that. Come on, quickly finish this. Parallelly, you draw this. Come on, everyone. Then find the centers of these circles. Okay. You will be knowing the centers of these circles. You mark the centers of these circles. Then, if you draw a line from the leading edge to the trailing edge, which passes through the centers of, or which is the locus of the centers of all these circles, that line will be the mean camber line. So I can see that this is the line which is passing through all these centers. Okay. So this line that we got now will divide the aerofoil exactly into two equal halves. Okay. So this line we will call as the previous one. This was blue line is your chord line, whereas this one is your mean camber line. Mean camber line. I'll refer to this as MCL. Right. Mean camber line. Mean camber line divides the airfoil into two equal halves. As shown in above figure. As shown in above figure. Okay. Now you write a heading, camber. Okay. Camber is nothing but some distance. Let's see what is this distance. What is the camber of an airfoil? So let me draw that same figure again. Okay. Those are previous figure that we made, in which we got the chord line and the camber line. So we have now the chord line as well as the camber line. So let me just erase all these unnecessary things. So we know that this is the chord line and you have the camber line. So let me take this and put it here. You draw this figure, everybody. So here you have two lines. This one is your chord line. And this one is your mean camber line. Okay. If you draw or you find at the distance between two lines, that is mean camber line and chord line, measured perpendicular to the chord, should be measured perpendicular to the chord. This distance is what is called as camber. Okay. Can I go ahead, everyone?
Yes, sir.
So you draw this and write the transverse distance. The transverse distance measured perpendicular to the chord, measured perpendicular to the chord line, measured perpendicular to the chord line between the chord line, and mean camber line is called camber. We'll go step by step. If you have any doubt, do not hesitate to ask. So every lecture, before class, in between the class or after the class, we are open for doubts. Okay. We are here to help you out. Okay. Fine. Everybody. Shall we continue? Guys.
Yes, sir.
So there are two things. So typically in aircraft, you'll have aerodynamic forces. Okay. If you will have a vehicle moving in water, you will have hydrodynamic forces. Okay. So if it is a fully immersed body in water, you will have hydrodynamic forces. And if the aircraft is in fully immersed body in an air, so we have aerodynamic forces. So apart from aerodynamic forces, you have many other forces also. Okay. So you have stiffness, you have shear force, you have these aerodynamic force has is a combination of pressure and stress. Okay, so we'll see all that. But typically on an aircraft, if you are having aerodynamic forces, typically they are one is lift and second one is drag. Okay, these are the typically aerodynamic forces you have. So you write a heading lift. What is lift, guys?
Vertical upward force.
This is the biggest mistake you will ever do in your aeronautical course. Okay. Lift is not an upward force. Keep that in mind. Okay. I'll elaborate that. The best way to say what is lift can be a downward force also. It can be a horizontal force also. I'll give you all those scenarios. So that is the first mistake, because once you do think that lift is an upward force, your aircraft performance stability becomes like not an understandable subjects. Okay, that is a very wrong statement. So you write lift is an aerodynamic force. Lift is an aerodynamic force which acts perpendicular to the relative wind. Okay. So how do we define this? Let me take that same airfoil. Okay. Let me take this airfoil. So there are different ways you should see it. So what usually a mistake happens is because people teach this with one way like this. So this is the most general way you will first listen to the lift. That's why you think lift is an upward force. Okay. So you draw this. So what is this? This is your chord line. Okay. This is your chord line. And let's say you kept this body in a wind tunnel and the flow is coming with a relative wind like this. So what is this? It is a relative wind. This is the flow which is coming with a relative velocity. You can say free stream for a while. So in this case, your relative wind is nothing but your free stream. So let's say flow is coming like this. So this angle between the relative wind and the chord line is what is called as angle of attack alpha. AOA, I use it for angle of attack. Is that fine, everybody? Can I go ahead? So if there is a force called lift produced, so how does the lift gets produced? There are so many ways of explaining how the lift is produced. We'll discuss that little later. There are many wrong explanations which are very widely circulated, that just the pressure difference or Venturi effect, all these things they will say. But you remember, there will be at any point on the surface, whether you take a point here, anywhere you take a point, you will have at any general point, you will have a pressure P. Okay. And there will be if the fluid is holded on the surface, there will be a shear stress like this. So what you do is, you will integrate this pressure and shear stresses, you will get one resultant. If you resolve that resultant R, okay, suppose you have a resultant force R after integration. If you resolve this force perpendicular to the relative wind, where I have done perpendicular to this. Okay, see, this definition cannot change. Okay, It has to be the same. Lift is a force which acts perpendicular to the relative wind. Now, if you resolve this R parallel to the relative wind, you will get a force called drag. Draw this, everybody. Around the whole surface, when you integrate P and tau, you will get these resultant force. If you resolve this, you will get lift and drag. Okay. So perpendicular to the relative wind, if you resolve, you get a force called lift. And in the direction of the relative wind, if you resolve, you will get the drag. Have you finished this figure, everyone?
Yes, sir.
Okay, let's go ahead. Write a heading, drag. So further we'll discuss lift, then we'll go for the drag. Okay. So here you have, if I just memorize this equation, I'll think that, like she said, lift is an upward force. Okay. But it's not true in all the cases. Now, let me take one aircraft. Okay. Let me take some nice aircraft for you. I hope I have some nice aircraft. So this is my aircraft. Okay. Now, if this aircraft is flying like this aircraft is flying. So what you do is flying from right to left. You make the airplane stationary and pass the relative wind in the opposite direction. How would be the relative wind will be looking like? This will be the relative wind. If you stop your aircraft and pass the relative wind in the opposite direction. Okay. So the aircraft is moving through stationary air, or the air is stationary and the aircraft is moving through it. Okay. So we made the airplane stationary and we are passing the relative wind in the opposite direction. So this, and if I draw the chord line, this will be the mean aerodynamic chord line. So this is your chord line, let's say. So here angles are very small, but you can see this is your angle of attack alpha. Okay. It's a positive angle of attack. The plane is going in straight and level, I am showing as of now. Later we'll change this. Okay. At this point, you draw lift. Our interest is lift in this case. Focus on drag bit later. You need lot of information to understand drag. So this is your relative wind, or you can say flight path also. If you are not making it to go like that, you can say this line is still as the flight path. You can say flight path, or lift is a force which acts perpendicular to the relative wind or flight path. Both are fine. Even if we stick to this figure also, lift is an upward force. Right? But that is not always. That's why the definition of lift is an upward force is just applicable to few cases. Okay. But lift is a force which acts perpendicular to the relative wind, will be applicable everywhere. Can I proceed, guys?
Yes, sir.
Okay. So this is a plane is in straight and level flight. Straight and level flight. The plane is not going up or down. It's flying in straight and level. Okay. Straight and level flight. You write beside that figure, straight and level flight. So these are the cases. Okay. Let's go to the next case. Let me take this. Now, if my aircraft is climbing, okay. If my aircraft is climbing, what do I have? Nobody is going to come and blow the air horizontally, okay? No air will come like this. God will not send a genie to blow that horizontal air. So what happens? Lift will get tilted like this. It's no longer just upward force. It's tilted now. Okay. Draw this. And beside this, you write B, climbing flight. Draw this. Try to make small figures. The angle of attack is positive in both the cases. Some students, they used to answer that in a straight and level flight, angle of attack is 0. It is not so. In fact, the case I am showing you here is the angle of attack in both the cases I am showing you same. If it is 2 or 3 degree in straight and level, here also alpha is 2 and 3 degree, and I am climbing. So with respect to this, if I measure the angle with respect to the local horizontal, and if this is my flight path, this angle is what is called as angle of climb, and it is denoted by theta c. It's called angle of climb. Make a note of that. That black line is your chord line. It will be mean aerodynamic chord line. I'll show you that little later. Once you finish it, let me know. Come on, guys. Don't try to become an artist. See, I made this figure by spending some time. Okay. Like I in my free time, I draw things like this. For me, this each and every part is different. Okay. You don't try to do that in one day. Okay. Can I proceed, everybody?
Yes, sir.
Okay. Now you take the aircraft. Let's allow it to glide. Okay. Now I'll make it to glide. So this plane is going to descend now from one altitude to the another. So I stop the airplane at its instantaneous position and pass the relative wind in the opposite direction. Okay. So its flight path is going down like this. The plane is going to go like this. So I am stopping it, passing the relative wind in the opposite direction. So this is also at a positive angle of attack. This is C. It's called gliding flight or descending flight or flight in descent. Make a note. In all three cases, I kept the angle of attack same. Can I go ahead, everybody? None of these angles are called negative angle of attacks. All are positive angle of attack. So alpha is greater than 0 here. Alpha is greater than 0 here. And alpha is greater than 0 here. They are not 0, not less than 0. They all are greater than 0 angle of attack. Many people think this is a negative angle of attack flight. That is a really bad way of understanding the negative angle of attack. Can I go ahead, everyone? Come on, be quick. So now you make one small extension here. We will add up something here. So you can simply add one local horizontal over here. Okay. Add one local horizontal like this and mark this angle. This angle is denoted with small gamma. It's called glide angle or angle of glide. Angle of glide. So with this, you should have understood what is angle of attack. It is the angle between the chord line. This is the chord. So mean aerodynamic chord, we are coming to that. What is mean aerodynamic chord? We'll understand that. Hope you all are through with this, everybody.
Yes, sir.
Okay. Now, right, the angle of, you write a small subheading, angle of attack. Then we will continue with lift. Angle of attack. It is denoted by the symbol alpha. I prefer calling it short form as AOA or small AOA. Okay. You write angle of attack. Angle between the chord line and the relative wind or flight path is called angle of attack. Is called angle of attack alpha, denoted by symbol alpha. Okay, which I showed in above figures. All 4 figures, 1, 2, 3, and this 4. This is what is angle of attack. Okay. Let's continue with what is called what is lift further. Then you write types of lift. How many types of lift exist, guys? For some of you already I taught this. Ashwin, how many types of lift exist?
2, sir.
What are those?
Static,
Very good.
dynamic.
Good job. Static lift. And the other one is dynamic lift. So let's see first what is a static lift. Okay. So, right, static lift is produced by lighter than air vehicles. Lighter than air vehicles. Examples of this would be airships or airships, balloons, etc. etc. Okay. So any vehicle which is lighter than air produces static lift. Okay. So we are interested in a dynamic lift. Right. So you write our aircraft is a heavier than air vehicles. Right. All aircrafts are heavier than air. So you write dynamic lift. Dynamic lift. Right. Dynamic lift. Dynamic lift is produced by heavier than air vehicles. Heavier than air vehicles. Okay. Examples of this would be aeroplane. Aircraft means it can be aeroplane also, it can be helicopter also, it can be drone also. Okay. Whereas aeroplane means it's a fixed wing. It cannot be a rotary wing. Okay. Aeroplane, helicopters, etc. Okay. So this dynamic lift is denoted by L. And by using dimensional analysis, we can prove that the formula for that is half rho V square S CL. This is our first equation today. Call this as equation number 1. Who is who? I'll give you that. So here you write where L is lift. Rho is the density at that height. Density of air at altitude h. V is the true airspeed of the aircraft. So when to use true airspeed and when to use equivalent airspeed, we'll discuss that after you understand what is true airspeed and equivalent airspeed. Okay, true airspeed of the aircraft. S is the wing planform area. It is not the surface area. Okay, wing planform area means what you see from the top view. Top view projection, you can say. What do you see if you have a wing in your hand and what you can project from the top view on a horizontal sheet? That is what is called wing planform area. Okay, plan view. What you see from the plan view. CL is the lift coefficient. It's a non-dimensional coefficient called lift coefficient. Hope you all are through.
Yes, sir.
Okay. So then you have here one typical thing S. This is our typical interest here. This S. Lot of people do mistake in finding this S. So S is given by P into C bar. So what is this C bar? This C bar is called as the mean aerodynamic chord. Mean aerodynamic chord. Okay. So first we will learn what is mean geometric chord. Then we'll come to mean aerodynamic chord. Is that fine, everybody? Okay. Then only you can find this lift. If you don't know how to calculate this C bar, you cannot get this S and you cannot get the lift. So our objective is to get the lift, right? Can I proceed now, everyone?
Yes, sir.
Write a heading. So before I proceed with mean aerodynamic chord, okay, let's look at few other parameters also. To find this mean aerodynamic chord, we will be working with some other parameters also. So for that, you need to understand what are the planforms. So you better write first various wing planforms. Various wing planforms. Then we'll come back to the aerodynamic force called drag. Okay. So did I mention there? Okay, I have mentioned that, but we will need to work first on finding the lift and many ways of doing that. Okay. Then we'll come to drag. So you write various wing planforms. In this you draw it like this. Yes, like, let me check. I have nicely pre-drawn figures. Let me just get those figures. Okay. So you start drawing this. Draw this wing planforms. So this is a rectangular wing planform, the first one. Okay. Then you go for trapezoidal wing planform. Come on. Start doing this. Start drawing all this. Then you go for sub-back wing planform. Step by step, you start drawing one below the other. Try to maintain the wingspan same. Okay. Keep their wingspan same. Okay. Then you go with the delta wing. Just let me just copy, then you can continue to draw. So for all these wings, I am keeping my wingspan same almost. That you need not have. You can have different spans, but for the sake of comparison, I need something common in between them. So I can draw it for the same area also. That will become a different story. Shall you start drawing now? Come on. So this one is a. So you can divide this. You can draw one line, straight line, passing through the centers. So it could be like just one dividing line kind of thing. 1 second, yes. I'll just change this. So you have the right side span and the left side span. So the right side of the wing is called as starboard. Okay. Right side of the wing towards its right, this portion is what is called as starboard wing. Okay. It's called as starboard, right side of the wing. Okay. And the left side is called starboard side, is right side. Left side, which is this, is called port side, port wing or port side of the wing. For every wing, it is like that. So the first one is my rectangular wing. The next one is turn off your somebody has switched on tapered wing. Then you would go for swept back wing. Same way you can have swept forward also. I'll draw that. Just beside this, I'll draw a swept forward also. Let me just ungroup this. We can simply rotate this and it will become swept forward. Some airplanes have this kind of thing. And this is a delta wing. Come on, guys. You draw this. Be quick. Come on, guys. Be quick. It's simple, small sketches. Have you made it till delta?
Yes, sir.
Okay. Then you go for the elliptical wing and make sure you don't draw one ellipse. So mostly these elliptical wings are made with, this is one ellipse and this is another ellipse. Okay. Using the combination of those two, well, mostly the elliptical wings are formed. Draw elliptical wing. Then we have many other wings which are like, you have double delta, you have notch delta, you have complex delta. These are different varieties of wings. Okay, so these are the most common variations of wing plan forms. Okay, come on, finish this elliptical wing plan form, then I'll go ahead. Can I proceed, everybody?
Yes, sir.
Rohan, Roshan, Brinda, I hope you all noted this.
Yes, sir.
Yes, sir.
Let's go ahead. Let me take any one of these wings, but before I proceed, let's continue on this figures itself. So if I draw, if I find this is the chord line. Okay. This is what this distance from leading edge to the trailing edge is what is the chord line, C. And the distance from one tip to the other tip of the wing, tip to tip distance, the distance between the two wing tips is what is called wingspan. So here C is chord and B is wingspan. Okay. So the planform area S for this case will be B into C bar. B into C. So C bar is C. No problem when you are having a rectangular one, but when it comes to the tapered wing like this, you have a problem there. So you mark here CT and you mark here, let me mark here CR. This distance is your CR. So CT here is the tip chord length. And CR is the root chord length. Okay. So why this wing is called tapered? Because CT is not equal to CR. Okay. So you have a See, whenever you have CT not equals to CR, it is called tapered wing. So even in this swept back or this swept forward, I have some taper ratio. So what is this new term I'm going to introduce is taper ratio. So when we write in this formula, S equals to L equals to half rho V square SCL, S is equals to B into C bar. But V length into breadth is good if you are writing or if you are having a rectangular wing at your hand. But here we are at hand, our problem is tapered wing. So how do we account for the area of that? Okay. So you write taper ratio lambda equals to CT by CR. So usually taper ratio lies between 0 and 1. Okay. Here, what was the lambda value? What is lambda value for rectangular wing? How much is the taper ratio for rectangular? Respond.
1.
1. Okay, so this is 1. And if I go down to this delta wing, what is its taper ratio?
0.
It will be 0 because CT is 0, tip chord length is 0. So taper ratio is 0 for a delta wing. So remember that this taper ratio, okay, let me just drag this one bit down. You can write these things around this figure. So this taper ratio of lambda lies between 0 and 1. Okay. If it is 1, you are having a rectangular wing. If it is 0, you are having a delta wing. Okay. So lambda is equals to 0. So here also you can show this is your tip chord, CT. And this is your root chord, that is your CR. You can mark CR here. Okay. Can I proceed, everybody? Hope you noted this part here.
Yes, sir.
So if you are having a tapered wing means this lambda cannot be equal to 1 and it cannot be equal to 1 or it cannot be equal to 0. It will be lying between 0 and 1, but not at the end points. Okay, let's go ahead. Write a heading, mean geometric chord. First we will see how to find the mean geometric chord. Mean geometric chord. MGC. Mean geometric chord. So depends on whether you are having an supersonic or subsonic aircraft. We'll take supersonic as of now. So let me take one typical plan form, semi-span of the plan wing I'll take. Let me just check through this 1 second. Oh, I don't have it. 1 second, guys. Let me. I spend a lot of my time on creating this figures which can help me to put things in a right way. Yeah. So draw very neatly one figure like this. Come on, everybody do this. Draw this figure as neat as possible, everyone. Draw y-axis and x-axis like this. So this y-axis in an airplane is your lateral axis. And x-axis is your longitudinal axis. I wrote longitudinal short form. You just note that longitudinal axis. Can I proceed, everybody? Hope you made this figure.
Yes, sir.
Okay. Now, this is your CT, tip chord length. And you draw here the root chord. Mark this as CR. Okay. Can I proceed? After doing this, you just measure half of the tip part and mark a line like this. Mark a point somewhere here. This is your CT by 2. Okay. Then you measure your half of CR. So that will be CR by 2. I'm looking it for the supersonic one. Okay. So you have CR by 2. Mark one point here. Join this point and this point. You'll get a line like this. So any cross section you cut like this will be half, this will be half, this will be half, this will be half. So this line, because of that, has a name, half chord line or C by 2 line. Call it as C by 2 line. Name it as C by 2 line. Okay. Then what you do? You measure this CR, length of this, whole length of your root chord. Copy that. Come to the leading edge of the tip. From there you measure this CR and mark one point here. Like this. Then you measure this CT and come to this trailing edge of the root chord. Okay. And mark one point here. Do that. Now you have these 2 points. Join this point and this point. You'll get one line like this. I maintained the colors also so that you understand which distance I have copied and where I have placed it. Okay. I'll get this point. And through this point, now you draw a line. Through this point, you draw a line which passes through this point and leading edge and the trailing edge. Okay. So this is a line which is parallel to your longitudinal axis. Draw such a line. Everybody do that. I have this line. So from here to here, I'll measure this distance. Okay. This is my mean geometric chord. And it is a very good design practice to take this itself as the mean aerodynamic chord very often. Okay. So this distance that you have here, from this to this, what is this distance? Can somebody give me this distance? From the longitudinal axis to this tip, how much is this distance? Guys,
B, right?
no, it is B by 2.
Half of the wing.
It is just the half of the wing, right? How can it be B? It has to be B by 2. Okay. So remember, you have taper ratio, lambda. So taper ratio here, lambda is CT by CR. Okay. So your mean geometric chord is this length. Okay. Hope you all did this. Can I go ahead?
Yes, sir.
Okay. Now you write one note. It is a good design practice. It is a good design practice to take mean geometric chord if it is a subsonic airplane, we will be having C by 4 line like this. Okay, and we will have mean geometric chord here if it is a subsonic airplane. Okay, fine. So you're right. It is a good design practice to take mean geometric chord equal to mean aerodynamic chord. Mean aerodynamic chord. So the question is, what is this mean aerodynamic chord first of all? MAC. We'll see that. Now we know MGC. Let's equate it to MAC and then we'll understand what is the usage of this, why we need such a thing. Can I proceed, everyone? Hope you noted this. Guys,
Yes, sir.
so now let me take this. Okay. So I have this as my, let's say, this is my C bar. Okay. So we got this as our mean geometric chord equal to mean aerodynamic chord I am taking. So I can draw a semi-wing with this mean geometric chord equal to mean aerodynamic chord. Let me just make it thicker. One second. Not getting nicely aligned. Okay. So now I'll get in for the same span. See, here I have not changed the span. Okay. Span is still the same. So this area is in clearly a rectangular area. Okay. So the area of the trapezium, which was half of the wing, okay, was, what is the area of the trapezium before? CT plus CR. See, if you have any trapezium like this, A, B, and height is H, how do you write its area?
1/2 A plus B into H.
A plus B into H by 2, right? That's what you said. Is that what you said?
Yes.
Good. So we have here such a thing. What you will get? CT plus CR into H is what? B by 2. By 2. So from this, we get only half of the wing. We are looking at only starboard, right? That's why I wrote S by 2. So from this, if I strike off this 2, I'll get the wing planform area clearly. Wing planform area S equals to, what do I get? CT plus CR into B by 2 I'll get. That's my wing planform area for this. Now, what is this purple color thing? It is the equivalent rectangular wing, which has area S equals to B into C bar. Hope I'm making sense. It isn't every time you use the formula L equals to half rho V square SCL, you are finding this equivalent wing planform area and you are having this. If you are using S equals to B into C bar, that C bar is mean aerodynamic chord. So this wing, equivalent rectangular wing, should produce the same aerodynamic forces and the moments as that of the actual wing. This is your actual wing and this is your equivalent wing. Okay. Now there would be another thing called this requirement called Y bar. Location, where is this? Okay, if you want to find this Y bar, you can take the moment of the area by considering a thin strip. Okay, this is Y bar. So you write Y bar, you write location of mean aerodynamic chord, MAC or MGC, is given by Y bar equals to, or you take the moment of the area. This area is S by 2, semi-wing, right? Into Y bar. About the longitudinal axis, you take about this axis, you take the moment of this area. This area is S by 2. S by 2 into this Y bar should be equal to, if I consider any y with a thin strip like this at a distance y, if I consider a strip theory and consider a thin strip with a chord length c of y having the thickness dy. This thickness is dy. This thickness is dy. And it is measured, kept at a distance of from the longitudinal axis at a distance y. Draw this, everyone. Then we'll take the moment of the area. So this line is your vertical, the line that I am drawing here is your longitudinal axis. This is your longitudinal axis, this one. Okay. So I'm going to take the moment of this thin strip about this longitudinal axis, and the area of this whole area, I'm going to take moment about y, the longitudinal axis. So you will be getting this. So you write taking moment of area about longitudinal axis. S into y bar equals to 0 to b by 2. What is the area of that small strip? C of y into dy. That is the ds. This is your ds. ds into y. Take this. So you will get y bar equals to 2 by s, 0 to b by 2, c of y into y dy. Bracket this thing. You call this as equation number 2. Call it as equation number 2. Or you call it as 3. There is one more important equation for which I didn't give numbering. Okay. Hope you finished till here. You give this equation a number 3. Okay, everyone. Can I proceed, guys?
Yes, sir.
Okay, see here, what we have is the taper ratio. You bracket this and call this as equation 2. One I gave for lift. Call this one as equation 2. Then you write area of the strip, area of thin strip is ds, that is equal to c of y dy. Okay, so integrating this ds, you can get s. From where to where you will integrate? Minus b by 2 to b by 2, which you can write as 2 times of 0 to b by 2. One side of the wing, if you calculate, the other side you can just multiply. It's a symmetrical wing. So you will get 2 into 0 to b by 2 c of y dy. That will be giving you the wing platform area. The other way around was you found it by using a trapezoid. This was the another way of finding it. Simply using your school basics. Call this as your I think you can leave this. Just bracket it. You can call this one as equation 4. Okay. If they give c of y as c as a function of y, this is one of the best ways to compute the location of mean aerodynamic chord and everything. Okay. Now coming to mean aerodynamic chord, C bar. Write a heading, mean aerodynamic chord. There's a nice theoretical expression which you can use to do. So you write, mean aerodynamic chord is given by given by or can be found by using C bar equals to 0 to B by 2 C of y into ds divided by 0 to B by 2 ds. That is equal to, or you can write minus B by 2 to B by 2 C of y ds divided by minus B by 2 to B by 2 C of y and or ds. Okay. So what this would become? ds is, what is ds? C into dy. So you can write this as minus B by 2 to B by 2 C of y into ds is C of y dy. And this is minus B by 2 to B by 2 C of y dy. Okay. Can I proceed, everybody? Hope I'm making sense. Respond, guys.
Yes, sir.
Let's go further. So from this equation, what is your denominator? The integration of ds is s, right? So you can write your C bar as 1 by s, the denominator I have done, minus B by 2 to B by 2 C of y square dy. That is equal to 2 by s integral 0 to B by 2 C of y dy. C square of y or cy whole square. C of y square you can write. C of y square dy. Bracket this. This will give you MAC, mean aerodynamic column. Call this as, it's a very good design practice to take this mostly first estimate as equal to the mean geometric coordinates. Can I proceed, everyone?
Yes, sir.
So that now once you know C bar, if you know C bar, you can multiply C bar with B and get the wing planform area. Using that wing planform area, you will be able to compute half rho V square S CL. Okay. So to find that S perfectly, you need to know C bar. And to know C bar, you need to know this formulas and the way we compute it. Let's go ahead. Now I'm slowly going to pitch into what is called as aircraft performance. Okay. So slowly we are entering into what is called as aircraft performance. Let's dig into this. So write some. The aerodynamic forces, that is what is called drag, we will discuss in more detail after a break. Okay. But not after a break, maybe next class. Today our main focus would be on the topic atmosphere, but you write few more things. So you write next drag. Just a definition and then we'll go ahead. Drag. So you write drag is an aerodynamic force. So if I talk in terms of sentimentally, what is drag? Drag is an enemy of the aircraft which tries to resist the motion, forward motion. But this drag is very, very necessary when you are coming for landing or you want to reduce your speeds. Okay, so this drag, your enemy of the aircraft has to act as your best friend when you are doing descending or decelerating or you are coming to land or landing. Okay, so drag is an aerodynamic force that acts in the direction of relative wind or you can say, which acts in the direction of relative wind or opposite to motion. Okay, opposite to motion. Where the aircraft is moving, if the aircraft is moving forward, the backward will be the drag force. Okay. So we saw how will be that drag already in the figure, right? So there are many varieties of drags. Now the aircraft has typical moments. Okay. We will discuss that. Moments. Okay. Moments. So you write the aircraft in general executes three principal movements about three principal axes. Okay. First about lateral axis. So you write first moment, pitching moment. Pitching moment. Commonly we write it as PM. It is the movement of an aircraft about the lateral axis. Okay. So it is a movement about lateral axis of the aircraft. Moment about lateral axis is what is called pitching moment. So let's see how this moment will look like. Let me take some nice aircraft for it. Draw such an aircraft, everyone. Come on, be quick. So about the lateral axis, if I make a movement about its, so this would be the moment. So the airplane is in this case, the airplane has got pitched up. This is called pitch up moment. Okay. This is the moment. So it would create a change in theta. Okay. So this moment, let's say this moment is about the CG. So you are taking a moment about CG of the aircraft. I pitch this airplane about its CG like this. So this is the CG of the airplane. This thing is your CG of the airplane. So this is the moment about this airplane. Okay, you can have plus M or you can have this plus M. If you are going down, that is called minus M, anti-clockwise. So this is what plus M means, is a pitch up moment. Pitch up moment. So you should not remember the moments by what do you call by clockwise, anti-clockwise. Rather, you just look at its nose going up. It's called pitch up. Nose up moment is also called as pitch up moment or positive moment. If it is minus M, it will be like this. It will make the airplane's nose go down. The whole nose will go down. Okay. So minus M is the pitch down moment. Pitch down moment. That is nose down. Hope you all made this figure. Can I go ahead? Okay, so remember this moment is about lateral axis. Okay. Now you write second moment. Right. rolling moment. Rolling moment. It is denoted by L in general. Lift also and moment also in aeronautics is denoted with L. Okay, rolling moment. Now let me take some nice aircraft for it. Draw an aircraft. So here I am showing you the rear view of the aircraft. Okay. So here this is a wing which is starboard wing. Right wing. That is right wing. And this one is the port. This is called port wing. That is your left wing. So if this wing rotates about longitudinal axis like this, rolls about the longitudinal axis, this is what is called rolling moment. Okay, so the moment, if the wing goes to the right side, okay, the wing goes to the right side, it is called plus L. Okay, fine. Here you have plus M, here I am showing plus L. So this angle that it creates is phi. The theta was pitch angle. So here theta was pitch angle. Mark that theta as pitch angle. Go back to previous figure. I totally forgot to give you a break. After just finishing one more thing, I'll give you a break. Okay. So at 8 o'clock, you please give me a reminder. I have a habit while teaching, I'll forget what is happening around, or I have this lapse of time, I'll forget that. Okay, this phi, you call it as roll angle. Okay, call phi as roll angle. You guys are my new batch that started with this. You guys are my 115th batch of GATE Aerospace. I am teaching this from since 2008, 2006 actually. Can I go ahead, everybody?
Yes, sir.
So this plus L is called positive rolling moment. Rolling moment. If you have minus L, that is the port wing goes down. Okay. If the port wing goes down, then you will call it as negative rolling moment. We'll add up formulas also. I just missed for the pitching moment. I'll mention them. First, you write this. So here, hope you have some space. So this pitching moment is equal to M, that is equal to half rho V square S C into Cm. Bracket this. What's the equation number, guys? Can somebody give me the number for this equation?
Sixth equation.
Sir.
Fine. To come to this and write the rolling moment. So rolling moment, which we call as L, is equals to half rho. If you get confused, you can add LR. Half rho V square S B into CL. Okay. CL. C small l. Capital C small l. This is not the lift coefficient. It is the rolling moment coefficient. Bracket this. I'll give you who is who in the end. Okay. First, I'm making your basics strong so that you will know what is rolling, what is pitching, what is yawing. What is wingspan? What is the wing planform area? What is true airspeed? What is pitching moment, rolling moment, yawing moment? What is the lift? What is drag? What are their coefficients? All those things. Can I go ahead, everyone? Come on.
Yes, sir.
Yes.
Advanced PM
What, ma? What happened?
pitching formula.
I am unable to hear you. Can you repeat that?
Pitching formula.
I gave that already. There will be C here, whereas in the rolling you will have B there, and here it will be CM. There it will be CL. Right, third one. Yawing moment. And about which axis you are doing this? This is the moment about which axis?
Longitudinal.
Correct. Is the moment about longitudinal axis. Okay. Now you write yawing moment. It is denoted by N. And it is a moment about directional axis. Moment about directional axis. So this directional axis will be the Z axis. And this moment about longitudinal axis is your X axis. Okay. And this moment about lateral axis is your Y axis. Please do that. In pitching moment, you write lateral axis, beside that you write Y axis. Okay. It's the moment about Y axis. And this is the moment about X axis. And this is the moment about Z axis. So you'll be seeing things from the top view now. So let me pull out one nice figure from my self-created library. Just a second, guys. Let me take some nice figure for you. Take this. Draw an aircraft like this. Rotate about the CG. Okay. So this angle is what is your yawing angle. Okay. We call this as psi. Or we mark with this psi. Psi is yaw angle. So there will be some rate of yaw at which you are yawing and all that we'll see later. So if your aircraft is having a moment developed something like this about its CG, where your starboard wing goes back, this is what is called positive yawing. So with respect to the pilot, if the plane is moving towards about its Z axis towards the right side, if it is rotating, the starboard wing will be going back and the port wing will be going forward. So that is called positive yawing moment. Okay, so you write plus N is the positive yawing moment. Minus N, you write negative yawing moment. So this N yawing moment is equals to N, that is equal to half rho V square SB into CN. You can write C capital N or C small n. It's better you write C small n. Bracket this. I believe it is equation 11. Check. Yeah, that was, no, 6. This is 7. And this one is 8. Give the number in space. Call this as equation 8. Any doubts so far? Rohan, are you there in class?
Yes, sir.
Are you getting this? You're also from mechanical. There are many people from mechanical also. Are you
Yes,
getting
sir.
this?
Yes, sir.
See, if you study a step by step like this, aeronautics is very easy. Otherwise, rocket science is very tough. Okay? Please don't miss out any classes, but it will be easy. Okay? I hope you know your father is my guru.
Oh, okay, sir. Yes,
He's
sir.
he's my professor in IIT. He was my gas dynamics.
Oh, that's very nice, sir.
Yeah, thank you.
Thank you, sir.
I'll help you in this. Don't worry. Fine, guys. See you all after a break. Is that fine? If you don't have any doubt, we'll meet after break. I'll join through the same link in 15 minutes. Is that okay?
Yes, sir.
Fine. Hello, everyone. Shall we continue? Everybody? Akash,
Yes, sir.
let's go ahead. There are three Akash in this batch. One is absent, I guess. So now we will start something called as atmosphere. Okay. Write a heading, atmosphere. This is your first chapter. What is an atmosphere, guys? I'm talking about obviously not the Martian atmosphere, Earth atmosphere. What is Earth atmosphere? Ashwin?
Gases that is surrounding the earth.
Correct. It is an envelope. Okay. So it is an envelope of gases surrounding the Earth's surface. Right. It is an envelope of gases surrounding the Earth's surface. The Earth's surface. Sri Mahalakshmi, are you there in class? Sundar?
Yes, sir.
Write a heading. So here we are talking about dry atmospheric air first. Let's discuss that. So write a heading, dry atmospheric. Dry means we are not talking about the humidity here. The moisture content means moisture is represented with humidity. So dry atmospheric air near sea level. Near sea level. So this is as per US standard. There is a US standard atmosphere. Okay, 1962. Fine. So you make one nice table. So there are different atmospheric tables like this. We usually refer to this one. Okay. So if you are conducting a experiment in laboratory, this values if you take, that will give approximate data. Okay, you should measure your pressure, temperature, density in your laboratory when you conduct experiments instead of just sticking to this data. Okay, so you write here, make it an open columns. The bottom don't close it. There will be a lot of things. Here in this left hand side column, you write a heading, constituent, gas, and formula. And here you write content, that is percent by volume. Percent by volume. Mention nitrogen. So the gases that are present, the highest content in our atmosphere is filled with this gas by volume. 78.084. 78.084 approximately we say 78%. Okay. Then you write oxygen O2 20.948. So we approximately write say 21%. Then argon AR 0.932. So if you sum up this itself will become 99 point something. Okay. So the remaining not even like points, not even 0.1% is the remaining gases. That is carbon dioxide, that is CO2, neon, Ne, helium. So why we are interested in atmosphere? Because we are going to have mechanics which is flight mechanics. Our flight will fly in this atmosphere. So we must know how the gases are and what are the layers and how to perform calculations and all that. Then krypton, then methane, okay. Then nitrogen dioxide, NO2, okay. Then nitrogen oxide, N2O, sulfur dioxide, ammonia, NH3, okay. Carbon dioxide already I took. Carbon monoxide you take. Carbon monoxide, CO, and iodine. Right. Make a note of this, everybody. Be quick and put a closure to this table. So the summation of all this, that is traces of each gases, when you sum up all this, okay. So you write like this: traces of each gas for a total of 0.003% by volume is this summation of all these gases. Okay. Can I go ahead, everyone? Hope you all noted this.
Yes, sir.
Okay. Now you take a fresh page, start at the bottommost point. Somewhere here you start. Okay. At the bottommost point, you start drawing. Draw it like this. Just draw one horizontal. So vertically, I'll be showing what is called as the altitude. Okay. So we will go like this. Draw like this. Okay. So in some regions, you will have troposphere up to 20, in some regions up to just 10. So mean is somewhere around 11 kilometer, we say, as per international standard atmosphere. So this data is collected by from different locations across the globe. They collected the data at different altitudes. They collected the physical properties of air, like pressure, temperature, density, okay, viscosity, all this. They collected it and they took the mean of it that made the international standard atmosphere. Okay. So you mark it like this. This is what is your tropopause. So mark this as tropopause. Okay. So below this is roughly taken as 11 kilometers. Okay, the mean will be taken as 11 kilometers. Okay. So this is the region in which mostly our commercial liners will find. So the commercial airliners, they usually cruise at altitudes. If it is a jet engine, turbofan engines, they fly up to altitudes of 12,300 or 12,500 meters. Okay, most of your commercial airliners will fly in this zone. So you draw it like this. Draw one simple aircraft like this and call it as commercial airliner. So you call it as commercial. Fighters can go above tropopause, much above tropopause, commercial aircraft. Okay. So let me draw some small tree or something like that. And this is where you will have some sort of mountains and all. So in this region is called as troposphere. The name of this region is troposphere. In this troposphere, as the altitude h increases, here h is 0. As h increases, temperature will decrease. It follows the inverse lapse rate. And majority of the clouds you will see in this, but there will be clouds above that region also. So clouds can exist up to in the stratosphere region also. Much above ozone also you can have the stratosphere. So this region, so that this decrement in temperature with increment in altitude will cease at about one layer called as tropopause. So the decrement will stop and the temperature will remain constant. So this is a region where you further increase the altitude, but the gas distribution is such that, and the phenomena are such that there is a constancy in temperature. So this atmosphere is also called as isothermal atmosphere. So there are other places also where you will see this isothermal atmosphere. So this is our lower stratosphere. This is a part of stratosphere. So this is lower stratosphere. Above that, what you have is there is a layer called ozone. So you draw one layer like this. It's not perfectly a straight line kind of layer. So in some, it's a pretty big stretch. Fine. So somewhere in between you mark here 30. Like that you'll have 40, 50. So I'm going to 50. This layer is what is called as ozone. It is a shield. So only the useful ultraviolet rays it will allow to enter inside. So this is where we survive, right? So this, because of this ozone layer, it absorbs the hazardous ultraviolet radiations. Okay, so you can write here, you write that absorbs solar ultraviolet radiations. Okay. Then somewhere here you mark 50. So above the ozone layer, then you will get above ozone layer, with the further increment in altitude, what will happen is, if you increase the altitude here, the temperature will again start increasing. Okay. So the reflected sun rays from the ozone, they will heat up that medium. So from here till this point, you are having what is called as stratosphere. So this whole region is stratosphere. Okay, this whole region is stratosphere. So this is a upper stratosphere. above ozone, upper stratosphere. So in this region, again, temperature will start to increase. This region is called as stratopause. Okay. Above the stratopause, you have a region called mesosphere. Okay. Up till 90 kilometer, it is a mesosphere. So you mark like this and mark, draw one line in this fashion. Call this as mesosphere. Hope you all are with me, everybody.
Yes, sir.
Okay. You called, Arvind, we didn't do this before, right?
No, sir.
Right, mesosphere. So this is the region where actually the outer particles, like outer objects like asteroids or meteoroids or any debris, when they fall into the atmosphere, they'll feel this as the densest region. And this is where they will burn off. All the meteoroids and the foreign objects will burn off here. Okay. Name them as meteoroids. So mostly they'll burn off in the mesosphere. So you label this as 50, this as 90. I hope you can understand that I'm not drawing the equidistant points and all. So I'm not even interested in it. Then above this, there is a huge distance. Okay. So after a very, very long distance, you have what is called as what you have above this. This is the region somewhere around 500 kilometers. So around 500 to 550 or 600 kilometers, you'll be out of the atmosphere. So this is a region up to which you have something called as thermosphere. This is called thermosphere. The temperature should be very high in this region. This is called thermosphere. Okay. And beyond this, it's called the outer fringes of the atmosphere. This is what is called as exosphere. And further away, if you go, there is nothing there. We say no substance. Okay. So from here, it's a combination of mesosphere, thermosphere, and exosphere. These three you combine. This region is called as ionosphere. Okay. In this region, you will have molecules will be in the dissociated form. So you will not have full molecules all everywhere. You will have several locations. You will have ions, positive and negative ions. So this is full of ions, this region. Okay, it's a combination of some part of mesosphere, full thermosphere, and some part of exosphere. Okay. So now you draw something called as temperature and versus altitude. This is the most important one. So let this be the altitude and let this be the temperature. Okay. So let's say you have this as some T naught that is equal to T at mean sea level. Okay. So from here, with increment in altitude, what happens is the temperature will decrease. This is the increment of altitude. So with increment in altitude, temperature will decrease and it will reach a value somewhere. It will reach a value around 11 kilometers. You mark this. It is at 11 kilometers. It will reach a value somewhere around 216. We will compute that. After reaching that value, it maintains the constancy up to somewhere around 23 kilometers or 28 also you can take. Mostly 20, 25, I would suggest, would give you good answers. And thereafter it increases slightly, and then the temperature really starts to excel like that, like this. So you are going in the upper stratosphere region. Draw like this, everybody. This would be somewhere around 25. This would be somewhere around 30, 32. And then you are going beyond this, like you have gone to, let's say, 50. Hope you all made this. Write a heading. Mean sea level properties. It will be meaningless to make the performance of the aircraft if you don't know where it is flying. Okay, the performance gets affected by these atmospheric conditions. So we need to know how to do all atmospheric calculations. So mean sea level properties. Mean sea level properties. In bracket you write as per ISA. ISA stands for International Standard Atmosphere. Okay, so here this I'll be using this as MSL, mean sea level, short form. So you write at MSL, pressure. At MSL pressure, we will denote with PMSL or P0. Remember, this P0 is not stagnation pressure, okay? Stagnation pressure is something else. Because in gas dynamics or thermodynamics propulsion, we use P0 for stagnation or total pressure, okay? So this is not that. 101,325 Newton per meter square, okay? Density of air is rho at MSL, which equals to rho naught, that is 1.2256 kg per meter cube. Okay. In temperature, T at MSL is equals to T naught, that is equal to 288, that is 288.15, but you take 288, that is fine. Or you can say 15 degrees Celsius. But in our laboratory, if you mug up this and use it for experiment, that is very, very bad thing. Because in Chennai, I am in Chennai, so in my lab, roughly approximately the temperature will be between 30 to 31 degrees Celsius in day. Okay. So then you write dynamic viscosity or molecular viscosity of air, mu naught, that is 1.714 into 10 power minus 5 kg meter inverse second inverse. Or best way is to remember Pascal second, best units. This is at not zero height. MSL means what is the height? 0. But this mu naught is not at 0 height. It is at, as per the temperature, it is at 273 Kelvin, that is 0 degrees Celsius. Okay. Mu naught is the dynamic viscosity coefficient at 273 Kelvin, that is 0 degrees Celsius, not 0 altitude. You have to bear that in mind. Now, you write hydrostatic equation. So this air that is present in the gas as a gas in our atmosphere, we assume it to be static. It is mostly static, right? So hydrostatic equation. So you write, it's also called as buoyancy equation. Hydrostatic equation or buoyancy equation. You can call this, you must know this equation, right? I hope you know this. dP by dH equals to minus rho g. So it's, if you are considering some sort of air column like this, as you are going up, this is filled with some gas. Okay? And as you are going up, your density is going to decrease. You will start feeling lighter and lighter. So if you have this kind of thing, as you are going up, you'll be getting this decrement. Okay. So here, if you are having one level, if you are at P1 and you are going to P2, okay, you will start feeling lighter and lighter. So you have this, the density of air will become, so the weight of the column above this point is less, whereas weight of the column above this point is more. Okay, so the weight will start to become, weight of air will start to reduce. That is what is pressure actually. Atmospheric pressure means the weight of this air column per unit cross section. So you have here, you can write this equation as, yeah, you just mark this as the equation 1. Call this as equation 1. Okay, you can write, or dP equals to minus rho g dH. Okay, can I proceed further, everybody?
Yes.
Yes.
So you write next subheading, equation of state. I usually say EOS. Okay, equation of state. So is P equals to rho RT. If I assume the A to be as a working as a perfect gas, I can write the equation of state is also working for it. So you call this as equation 2. Now we will assume one more thing, that for air working as a perfect gas, what is this? R is 287 joule per kg Kelvin, where R is given by R universal by molecular weight. Okay, this is 8314 joule per kilomole Kelvin, and molecular weight is MW, which is in kg per kilomole. So the units of this are, which will be 8314 divided by MW for each gas, for any gas, that is for air. This is for any gas. Okay, for any gas, R will be this. The units will be joule per kg Kelvin, kilomole, you can give it. Okay. Hope you all noted this. What is MW here? It is the molecular weight of the gas. Here your gas is air. If you know R, reverse way, you can you tell me at least what is molecular weight of air? Come on. 8314 divided by
30.01.
30 or 20 something. Check that again. Check this again.
28.9.
Why it changed suddenly?
Instead of 287, I put 277, sir.
Okay, 28 point.
9.
One more decimal. 28.9. Is it zero there?
28.968.
Okay. So you stick to 968. Okay. That is kg per kilomole. Fine. 28.968 kg per kilomole is the molecular weight or molar mass, what you said. Okay. Right. Next heading. So now we want the tropospheric. First in our atmosphere, what we have? Troposphere. So we will be doing calculations for this region first, then we'll go for this. Okay, above that, we are not doing space missions as of now, so we don't worry about that. So you write a heading, tropospheric calculations. So what equations will work and all that, you know. So between the altitude ranging between 0 and 11 kilometers, you are allowed to use these equations. So we have two equations. From equations 1 and 2 in this atmosphere, from equations 1 and 2, what we can write? dP is equals to minus rho g dh. And by equation of state, P is rho RT. So you can spike off rho and you can write dP by P equals to minus G upon RT dH. Okay, bracket this, call it as equation 3. We will keep using this again and again. Call this as equation 3. Okay. It's already 9:30. Bear with me, guys. I don't want to stop till I finish this topic. Okay. Write a heading, lapse rate. At least tropospheric calculations will finish off. Lapse rate. All right. In troposphere, temperature decreases with increase in altitude h, following a lapse rate lambda, which is given by lambda equals to minus dt by dh. Bracket this. You call this as equation number 4. Okay. Now, in this troposphere, means between this 0 and 11 kilometers, I am drawing a small schematic for different altitudes. So this is, let's say, MSL, means sea level. So here you call this as H1. Here P1 is equals to P0. P1 equals to P0 and rho 1 equals to rho 0. When I go to a height H2, okay, when I am at height H2, the pressure here is P2, temperature is T2, density is rho 2. Okay, this H2 be equal to some H. Do that so that I can have some general relation between them. So I can write this, I can write dt equals to, from equation 4, I can write dt equals to minus lambda dh. So integrating this from T1 to T2. Here you have to place the units H1 to H2. So you will get T2 minus T1 is equals to minus lambda into H2 minus H1. So here T1 is T naught, H2 is H, H1 is 0. So I'll get T2, let this T2 be equal to some T at that height. So I can replace this T2 with some general T at a height. So you can write T equals to T naught minus lambda H. Very important expression is. Bracket this. Call this as equation number 5. Hope you all are with me, everybody.
Yes, sir.
Okay. Just few more steps and we'll be through with this, guys. I don't want to stop in the middle of this tropospheric calculations. Please bear with me another 5-10 minutes. Okay. Right. So from this equation 3 and 5. Okay. So you write from equations 3 and 5. From equations 3 and 5, we can write dP by P was equal to minus G by R dH by P. T is T naught minus lambda H naught. Now we got it as a function of H. Now I can integrate this from P1 to P2 and I can integrate this from H1 to H2. So this will become ln P2 minus ln P1 equals to minus G by R ln of T naught minus lambda H divided by derivative of this term will be minus lambda. Okay. From H1 to H2. Substitute. So this will become ln of P2 by P1 equals to G by lambda R ln of T naught minus lambda H2 minus ln of T naught minus lambda H1. Okay, if I make use of this, I can write T2 equals to T naught minus lambda H2 and T1 equals to T naught minus lambda H1. So I'm going to make use of this in below. You better write beside the equation 5 this thing, everybody. We are almost through with today's lecture. Just 4 more minutes, I'll wrap up. Can I proceed, everyone?
Yes, sir.
So what do I get here? I'll get ln of P2 by P1 equals to G by lambda R ln of this will become T2 minus ln of T1. That will become, please place that proper bracket space. So this will be ln of T2 by T1 whole power G by lambda. Can I write like that? Right hand side. And my left hand side is ln of T2 by P1. So I can take anti-log on both sides and I'll get, therefore, P2 by P1 is equals to T2 by T1 whole power G by lambda R. So with this formula, between any 2 points in troposphere, you can find the pressure. Pressure ratio you will get. And that you will get the pressure. So you call this as equation 6. We all know the equation of state. So by equation of state, you can write P2 equals to rho 2 R T2 and P1 equals to rho 1 R T1. So I am interested in getting rho 2 by rho 1. Rho 2 by rho 1 will be P2 by R T2 by P1 by R T1. RR if you cancel out, you'll get P2 by P1 into T1 by T2. So I already have this P2 by P1 as a function of T2 by T1. So I can write, therefore, rho 2 by rho 1 equals to P2 by P1 is T2 by T1 whole power G by lambda R. And this T1 by T2 can be written as 1 by T2 by T1. Substitute that, you'll get rho 2 by rho 1 equals to T2 by T1 whole power G by lambda R minus 1. Bracket this. Call this as equation number 7. Okay. Hope you all understood this. Any doubts so far? We are through with today's lecture. We'll continue in tomorrow at 6:30 p.m. Okay. Any doubts, guys?
No. Harish, Brinda?
Sir, is there any Indian standard atmosphere?
No, ma, we don't have as of I never heard about it.
Okay.
We follow the data from, but there would be, but it is not. I'm not aware of it. But the Indian Meteorological Department might have done some survey, but it is not. I have never come across it. These guys follow mostly. So if we make or if we have one, we would be having very accurate information about the predictions of weather forecast and all. We can do very nicely. Okay, so I'll check that and get back to you if there is a mic.
Okay, sir.
Any doubt? Any other doubt, guys? Please ask
No,
it.
sir.
Yes, ma'am. Yes, you can ask. What it is?
No, sir. I was saying I don't have.
Okay, fine. Fine, guys. Then see you all. Thank you so much for bearing patience. See you tomorrow at 6:30 p.m. Okay. Those who are new, very warm welcome to all of you for GATE PATHSHALA course. It's a very long and very strong journey for aerospace engineers here. Okay. Fine. Thank you so much, guys. Bye-bye. Good night.
Thank you,
Thank
sir.